So let's get started for the day. Today's topic is dynamic programming under certainty, which is summarized in chapter 4 of the textbook, and this is one of the most important and key chapters of the textbook. To see why, uh, let's summarize what we know. We are interested in dynamic optimization problems that can be put in two related ways. One is the sequential problem and one is the functional equation. When we put a dynamic optimization problem in the sequential form, we are trying to find an optimum policy, an optimum path, pattern, or program for the state variable, for the endogenous state variable, that helps the agent to attain the maximum level of satisfaction. It's important that these steps, this program must be feasible. So when the control variable is next period's state, it's important that these steps must be feasible. The same problem can be put in the form of the functional equation, the famous Bellman equation, which is a functional equation, meaning that the unknown in this equation is a function, the value function. We saw last time that when solving such a Bellman equation or functional equation, we receive a policy function and the value function, just like in the previous case of the sequential problem. So we have the policy function, the optimum utility maximizing policy function, and the supremum function. So the problems, dynamic optimization problems, can be addressed in two related ways, and it's essential that solutions to the problems, to the same problem put in different ways, must coincide. So it's essential, it's more than essential, it's key, it's crucial that when we address a given dynamic optimization problem, either in the sequential problem form, or in the form of the functional equation, we get to solutions, we get to the results where the results are the same whether we address the same problem in the sequential form or the functional equation form. This is the reason why chapter 4 is so important, because Stokey and Lucas clarify the assumptions that ensure that we have the same solutions either we solve the sequential problem or the functional equation form of the same optimization problem. So shortly put, we need to clarify the assumptions by which we will have one unique solution to the functional equation, which is the same as the supremum function of the sequential problem. It's not too difficult to realize that the supremum function of the sequential problem is unique. It must be unique, but the functional equation may have multiple solutions, so we need criteria by which we have only one solution to the functional equation, which is the supremum function of the sequential problem. So chapter 4, dynamic programming under certainty, is key because this chapter gives us the criteria in various cases. First, we will have the criteria in general. Actually, this is assumption 4.1 and 4.2. So we are going to have two assumptions and four theorems, theorems 4.2 up to 4.5. These assumptions and these theorems give us the necessary and sufficient conditions for correct solutions to any dynamic optimization problem. And the upcoming sections actually, bounded returns, constant returns to scale, and unbounded returns give us the same or equivalent assumptions that can be used in various cases where the assumption, some of the assumptions, some or all of the assumptions, not all, some of the assumptions of the baseline case don't hold.
Okay, first of all, let's have a look at what it means when the solution to the sequential problem and the solution to the functional equation or the Bellman equation coincide. Let's have the cake eating problem as the example. If you remember, we solved the problem, and a part of the solution was the value function of this form. This is the remainder part of the example. So this was our value function that described the maximum value of the agent he or she can gain from consuming this is not x0, let it be w0. So this was the value function that describes the maximum or optimum value the agent can gain from consuming a given cake by the optimum, by following the optimum path. And this was the policy function of the same problem. So we said that by following this policy function, the agent can gain the maximum value of consuming the cake, and this maximum value was described, or this is described by this value function. So let's have a look at what it means that the solution to the sequential problem and the solution to the functional equation or Bellman equation coincide. So if we go back to the previous slide, in general, this is the way we attack a problem with the Bellman equation. So this is the Bellman equation of a similar problem. On the left, we have the value function, and on the right, so this is the value function, and on the right, we have the same value function. And by maximizing this equation, so by finding the optimum policy, the optimum step, we need to satisfy this equation. So let me show you what it means. So if we have this value function, so this is the value function of the problem, of the cake eating problem. Hopefully it's correct. This is the left hand side, and this is the right hand side. So okay, this is supposed to be a beta. It looked terrible. Yeah, and the last item. So this is the problem we are supposed to solve. So we need to find the optimum cake size for the next period. We have the solution, so we know that this is the optimum cake size for the next period given the initial cake size. So we have this solution, so we can put this policy function into the Bellman equation. So let me expand the right hand side. With the left hand side we have nothing to do. If our solution is correct, so if this policy function is correct, by maximizing the right hand side, which means that by putting the policy function into the right hand side, we must have the same function on the right hand side as we have on the left hand side. Okay, so let me do the math, which is very simple. So let's start. This is the substitution. So instead of W1, we use the policy function. Later today, we are going to get back time and again to the same problem. Okay, I think it's correct. So this is just to be on the safe side. Okay, I don't need this bracket. Okay, so this is the left hand side and hopefully it's correct. So let's go on. All we need to do is to expand the right hand side of the equation. Okay, I think it's correct. Let me double check. It seems to be okay. So this is a sum of 1, 2, 3, 4, 5, 6 items, and we can look for similarities. So let's try to sum up the items with W0 Alright, this is 1 over 1 minus beta. And, you know, this is what we need. So, this is what we actually have. So this is alright. Next item is the next sum is the items with 1 minus beta. Okay. It's very similar. One over 1 minus beta, and let me check, let's check. It's correct. It's correct. And the fourth, not fourth, third item yes, this is what we need. It's a bit more complicated, so, but it's not complicated, just a bit more complicated. So let me skip the steps. You know, and trust me, this is the result, and let's check it. And it must be no. Okay, I am just confusing the things. So this is, and this is what we have at the bottom of the page. Okay. Okay, let's check. So let's do the classic steps. Okay, this is correct. This is correct. Okay, let me double check. Yep. Some items can be simplified. So what we have yep. so the result is correct. Okay, so now we can say that the right hand side under the optimal policy is the same as the left hand side. So this is the sense in which we say that by solving a dynamic problem, we have a functional equation, a value function and an optimal policy, and under the optimal policy, the two sides of the Bellman equation must coincide. Okay.
Now let's see what we can do about um, ensuring that solutions to the functional equation and solutions to the sequential problem coincide. So the main idea, the leading idea is straightforward. A solution to the functional equation, so a solution, a value function, evaluated at the initial state gives the supremum of the sequential problem starting from the same initial state, and the sequence attains the optimum in the sequential problem only if it satisfies the functional equation. So this is the way we set the idea that the solution to the functional equation and the sequential problem must be unique in terms of value function and optimum policy. The section starts with two key assumptions. Assumption 4.1 is very simple. The feasibility set must be non-empty at any state. It means that at any state there must be at least only one possible feasible choice. So at any state the agent must be able to make a decision. So the feasibility set mustn't be empty. And assumption 4.2, for any initial state and feasible policy, this limit must be existent. It doesn't tell much for the first sight, but assumption 4.2 is the same key and crucial as assumption 4.1. If these two assumptions hold, we say that any dynamic optimization problem is well defined because, one, there is at least one feasible plan. I'm repeating, so if there is a feasible plan at any state, the optimizing agent can make a decision at any state, and what is more, the value of the plan or plans can be measured and compared by the sum of one period returns. So this is the reason why assumption 4.2 is so important. This gives us the measure by which we can measure and compare the value of plans. Okay, so we have assumption 4.1 and 4.2, and on this basis we are going to set up 4 key theorems, and all these theorems contain additional constraints, additional criteria by which we ensure the uniqueness of the solution to a dynamic problem. Theorem 4.2 says that if these assumptions hold, then the supremum function satisfies the functional equation. So if we don't need to solve, actually, it's not necessary we actually solve the sequential problem, but if these two assumptions hold, the supremum function satisfies the functional equation, so the supremum function is a solution of the functional equation. There is a problem at this point. Okay, so the value function coming from the sequential problem is a solution, is one solution to the functional equation, but nothing guarantees at this point. There is no guarantee that the functional equation doesn't have further further solutions. So Theorem 4.3 gives a further criterion by which we can ensure that the functional equation has only one solution that coincides with the solution of the sequential problem. And this is a limit. If this limit holds, so if at period n evaluating the possible solutions to the functional equation at period n, the limit must be 0, the value must be 0. And there is only one solution to the functional equation that meets this criterion. So by abiding by this criterion, we can exclude, we can rule out any other solutions to the functional equation. So this is the reason why Theorem 4.3 and the criterion is so necessary. By abiding by this criterion, we can disregard, we can rule out any further solutions to the functional equation, and in the end we will have only one value function as the solution of the functional equation, and this only one, this unique solution is the supremum function itself. So by assumptions 4.1 and 2 and theorems 4.2 and 3, we have ensured that the value function solution of the sequential problem and the functional equation coincide. But so far we haven't done anything about optimal programs or optimal solutions, optimal policies of the dynamic optimization problem. So in Theorem 4.4 and 4.5, we need to do this part of the job. Not too surprising, we are going to have further assumptions. So let's assume that the state space, the gamma, x is the state space, gamma is the feasibility set, f is the one period return function, and beta is the discount factor. So let's assume that they meet assumption 4.1 and 4.2, and if we have a policy, a plan, a program that attains the supremum for a given initial state, then for any t, this plan satisfies the functional equation. This is a condition which we need to meet, but it is insufficient in itself because Theorem 4.4 doesn't rule out other feasible plans that also satisfy the functional equation. So a final criterion is needed, and this is given by Theorem 4.5. If assumptions 4.1 and 2 are satisfied, and if we have a feasible plan, not the optimum plan, not optimum plan, just a feasible plan, any feasible plan that satisfies the functional equation, and this plan satisfies this limit, then this is the optimum plan for attaining the supremum in the sequential problem. So once again, in the next slide, I will show you an example to better understand how these assumptions and theorems work. So to sum up at this point, by having these two assumptions and these four theorems, we ensure that the solution to any dynamic problem is unique in terms of the value function and the optimum policy.
Okay, let's have two examples to better understand how and why Theorem 4.3 and Theorem 4.5 work, and how and why they are important. According to Theorem 4.3, the functional equation may have multiple solutions, but there is only one solution that satisfies this criterion, and I want to show you what it means. This is the one thing we will do now. And according to Theorem 4.5, if we have a feasible plan, that satisfies the functional equation for any t, and the plan satisfies this criterion, then it is then x, so the plan is an optimal plan, and it attains the supremum. So let's have two interrelated examples to show how these two theorems work. It's a version of the cake eating problem. We have the initial wealth x0, and in this case, consumption can be unbounded, which means that the agent is allowed to finance consumption out of debt. So she can fall into debt. We have the rate of interest, where beta is in this interval, and this is the problem the agent solves: to find consumption and stock path that maximizes lifetime utility. Okay, supposing that consumption cannot be negative and must be lower, cannot exceed actually, this threshold. So okay, just to be specific where it comes from, so it's a savings problem. So in period t, the consumer, the agent, decides on the savings. Okay, and if we expand this equation, by using the rate of interest, we will have this equation. From which we get to the equation that describes consumption. So what you can see is consumption can be increased by falling deeply into debt. So consumption is unbounded. As consumption is unbounded, starting from any x0 initial wealth, any level of consumption is achievable. So the supremum function is infinity at any initial wealth. This is the supremum function. Now let's have the functional equation. This is the one period return function. This is the one period return function. And this is the correspondence, the feasible set, the feasibility set. So next period wealth can be very low. So it's not bounded from below, but it's bounded from above, as consumption is the difference, is this difference, and the upper bound for y, next period stock, is where consumption is 0. And if consumption is 0, then this equation holds, from which we have this equation, and this is the equation that describes the upper bound for the feasibility set. So the functional equation on this ground, the functional equation is this. We cannot use the max operator because we don't know if the maximum exists, because we don't have a specific utility function. Okay, so what we can see is this supremum function satisfies the functional equation. So Theorem 4.2 holds. There is no problem. What we need to check now is whether the functional equation has other solutions, and it does, because this is also a possible solution for the functional equation. Let's check it. So at any y x equals x, so no matter what policy we follow, this value function satisfies this value function satisfies the functional equation. And here is the point. If the agent follows this policy for every t, for all t, then we need to try to describe wealth dynamics, and in this case it is very simple. So this equation describes wealth dynamics under this policy. In this case, however, the criterion of Theorem 4.3 looks like this. Which is not zero if the initial wealth was positive. So Theorem 4.3 doesn't apply. It means that this solution for the functional equation is a solution for which it applies. So this solution is ruled out by the criterion under Theorem 4.3. So let's go on with this example to see how Theorem 4.5 works. So let's have the same example, and let's try to check why the criterion under Theorem 4.5 is needed. Everything remains the same as previously, but now we don't allow the agent to fall into that. So now we have this bound on the on wealth dynamics, so it cannot be negative. Wealth cannot be negative. It means that we have the problem in this form. Sorry. Because saving is still possible. Okay, saving is still possible, so it's still true that the agent, by not consuming a portion of his wealth, can have some income from interest, from the interest rate. So it is still true. It is still true. And it is also true that next period capital stock or wealth is maximal, where consumption is zero. So it comes from the previous case. It is also true. But what is new, what is novel, is that is not allowed, so this inequality must hold. So this is the new element in the setting. So we have a new correspondence, policy correspondence, not policy, sorry, feasibility set. Next period's capital stock cannot be negative. So this is the point. This is how we modified the setting. And x0, the initial capital stock is given. Let's expand. Let's expand the objective function. And it's gonna be fun. Because it simplifies the problem. Okay, and we can cancel some elements. So in the end, the supremum function is this, because all other elements just fell out. So this is the supremum function. As we saw, this equation satisfies the functional. This function satisfies the functional equation. It was, just a kind reminder, it was the solution of the functional equation we examined a couple of minutes ago. So, now let's have a look at the plans. What plans attain the optimum? What plans give the consumer the higher level of satisfaction? The consumer has options. So, for instance, this is a feasible plan. It means she consumes everything, consuming everything in T0 and leaving nothing for the later periods. Or another option. Maximum, not consuming everything, not consuming anything, sorry, not consuming anything in T0 and consuming in T1. Or a third option, period T consumption. First period, second, third, sorry, 0. We start 0. This is T0, T1, T2, and 3. And you can see there is nothing in period 3, so the consumer consumed everything in period 2. All these plans, all these programs satisfies the functional equation, and all these plans, all these programs give x0 satisfaction for the consumer, because we have this supremum function. So no matter what plan the agent follows, no matter what plans, what plan she chooses, she will have this level of satisfaction. So it's all the same when the agent consumes. However, if she never consumes, and this is the point, she always has a positive balance by repeated investment, which means she never has any utility. Simply put, there is never any consumption, and the criterion of Theorem 4.5 is positive for any positive initial wealth. So this is the way how the criterion of Theorem 4.5 ensures that a feasible plan is optimal. So even if a plan is feasible, no consumption cannot be optimal for never giving any utility for the agent.
The next special case in which we investigate how to address and how to solve dynamic optimization problems is the case of bounded returns. Just to go back to section 4.1, it's clarified that there is a way of ensuring that assumption 4.2 holds, and this is a very simple case in which we have bounded return functions. And on this basis, section 4.2 shows why it is so comfortable to have bounded return functions. So we will see in this section how and why bounded returns are so helpful. First of all, we will have two another assumptions, assumption 4.3 and assumption 4.4. According to the former, the state space is a concave subset of the L-dimension Euclidean space, and we have a correspondence gamma which is non-empty, compact valued, and continuous. Compact valuedness means that for any state, gamma is a compact set, so practically any closed interval will do, and gamma is continuous means that gamma is upper and lower hemi-continuous. Practically, you will see that it helps. Practically, any gamma with upper and lower bounds described by continuous functions will do. So we need practically any correspondence with closed interval given by continuous functions will do. Assumption 4.4, the one-period return function is bounded and continuous, and beta, the discount factor, comes from the open interval 0, 1. And under these two assumptions, assumption 4.3 and 4.4, assumption 4.1 and 2 hold, and more importantly, theorems 4.2 up to theorem 4.5 work, and they ensure that the solutions to the functional equation and the sequential problem exactly coincide. So all we need is to set up a problem in which assumptions 4.3 and 4 hold, and this solves the problem. So if we have a problem in which everything is formalized, including the correspondence, the return function, everything is formalized in a way that assumptions 4.3 and 4 hold, we are going to have a unique and appropriate solution. Section 4.2 is important because we have a bunch of further results. I don't want to go over these results because everything is contained and expressed, described appropriately in the textbook. So we have a number of assumptions under which solution v to the functional equation is strictly increasing, strictly concave. But there is one point I want to emphasize, and this is the famous and very helpful, extremely helpful Benveniste-Scheinkman formula. They showed that under specific assumptions, of which it is the concavity, strict concavity of the value function is the most important, it is possible to calculate the first derivative of the value function with the first derivative of the one period return function. It is a very straightforward analytical tool, analytical device, because when solving the functional equation at the stage of deriving the first order conditions, we go to a stage when we always go to a stage when the first derivative of the value function on the right is needed. And as we work with a functional equation in which the value function is the unknown, we cannot calculate the first derivative of something we are looking for. So the Benveniste-Scheinkman formula offers a bypass through which we can calculate the first derivative of the value function by the first derivative of the one period return function, and we will use the Benveniste-Scheinkman formula extensively in the upcoming lectures and seminars, so you will see how extremely useful it is. Okay, last but not least, let's have a look at unbounded, the case of unbounded returns. Sometimes it happens that assumptions 4.1 and 2 hold, but theorem 4.3 doesn't. It means that assumptions 4.1 and 2 ensure that the supremum function satisfies the functional equation. So in other words, the supremum function is one solution to the functional equation, but for the lack of boundedness in the sense of theorem 4.3, the functional equation may have other solutions, and in such a case we need another approach or other approaches, and theorem 4.14 gives us such an algorithm. The whole idea is very simple. We are supposed to find an upper bound for the supremum function, and if we start iterating from this upper bound, we can only go downwards. So we start iterating downwards, and at the end of iterating with the Bellman equation, we will find the solution to the functional equation. So we will find v as the solution, the appropriate solution to the functional equation. So as a last example for this lecture, let's have an exercise in which I can show you how to use this very powerful algorithm given by Theorem 4.14.
Okay, let's have an example to see how we can treat problems in which the return function, the one period return function, is unbounded. First, just as a reminder and context, let's go back for the cake eating problem. Actually, formally put, it is an economy with no growth, and in which we had this utility function, the simple logarithmic utility function, but C consumption cannot be zero, because if consumption, period t consumption, goes to zero, utility goes to negative in infinity, so the return function put in this form is unbounded below. This was a problem. Another problem that we solved the problem, the maximization problem, the optimization problem, by iterating on T1, T2, T3, as you remember, and we realized a pattern during this iteration. And at the beginning of this lecture, we checked that the value function we found, it actually solves the functional equation. But strictly speaking, our solution was only a guess. And as the one period return function is unbounded, it must be treated as such. So the point of this exercise is to see what we can do if the return function is unbounded. Another context, please check exercise 5.2, which is the cake eating problem in the book, in the textbook, and there the cake eating problem is solved with the algorithm of section 4.4, so of this section. So let's have the example. So this is the context. So let's turn to the example of page 93. This is a very simple growth model. We assume that there is an initial capital stock, and we assume that there is an optimal plan. And first we need to check if the limit of assumption 4.2 exists. So we need to check if assumption 4.2 holds. So how to do this? Let's try to have a pattern transition equation. So we know that this transition equation holds, and we have this utility function, and we know that consumption is the difference between period t production and next period capital stock. So the one period return function, it's no surprise, I promise, one period return function is this. So we have the explicit form of the one period return function. We're gonna use it. We know that next period capital stock cannot be higher than this period's output, which means that it is true, it holds. So this inequality implies this inequality. And it applies to OT, from which it comes that this holds and this holds, and we can go to any t and we can say, sorry, oh geez, yes, so this is true, and we can go to infinity and we can say that this is also true. So by using this inequality or upper threshold for the capital stock in period t, we can find a bound for the one period return function at any t. Given that this is the one period return function, we can try to find a limit, a threshold, a bound, and it is true. It is also true, and it is also true, and it is also true. All right. And from all this, it follows that we have this bound for all t. All right, that's okay. So from this inequality, we need to prove, and this is the question, we need to prove if this limit applies for this return function. Okay, so once again, now as a first step, or step 0, we are checking if assumption 4.2 holds. So let's try to do something about this limit. We use this form of the return function. In the lectures, we didn't cover this form. See page 64 to see how this function is defined. But it is related, so we didn't do anything which is not permitted. It's just a form. Okay, another form. So we are using this bound. Yep. Which is this threshold. So this is what did we do now? So this is the upper bound for the supremum function. So we can say, we are justified to say that the supremum function cannot exceed this threshold, this bound. All right. So we can say that the limit exists and it is finite. So assumption 4.2 applies. So what we can say now is that assumptions 4.1 and 4.2 apply. And now we can explicitly state this upper bound for the supremum function we need to use in the algorithm of section 4.4. Okay. So this is the absolute maximum value of the supremum function by which we are starting the iteration. So let's turn to the Bellman operator. So we are starting to iterate on the value function by using this upper threshold as the algorithm of section 4.4 requires us to do. Sorry. Yeah. So this is where the upper bound comes into play. Okay. Yep. It's correct. I'm just checking, and yes, it's correct. So we need to find the optimum value of next period capital stock. So we have the decision variable y, and we need to derive the first order condition with respect to y next period capital stock. So let's try to set up the first order condition. We are differentiating the functional equation with respect to y. I won't do the whole process because it would be terribly boring. So this is a intermediate step. And in the end, after a few steps, we will have this policy function. This is the optimum choice. By the first order condition we gained from the functional equation. So after the first stage of iterating with the Bellman operator, we will have this equation. I won't do the whole sequence of operations. You can do the math easily, so you don't need me to show all the steps. And after a few steps, we can, okay, let me be consistent. You will see that the textbook also uses f and v quite interchangeably. So after one iteration, this is where we are. Okay, so we have the result, the outcome of the first iteration. Let's use the operator again. As we are iterating on the upper threshold, upper bound for the value function. Okay. Now we are using, as the value function, we are going to use the outcome of the first iteration. So here you can see, I will highlight it in a minute. So we have put this value function into the functional equation of the next round. Okay, we want to maximize the functional equation, so we're gonna do the same. We need the first order condition, and it's interesting, not too interesting, but still, we have the same first order condition. So in the next step, in the present step, the same policy proves optimal as previously. So it doesn't take too much to write the explicit form of the second round of the iteration. We must be careful not to make any mistakes. It's quite mechanical. Okay? So this can be simplified into this value function. So this is the outcome of the second round of the iteration with the upper threshold. Hooray! Okay, all right. Some patterns are emerging, but to be on the safe side, let's make a final iteration round. It's gonna be decisive. We have the same policy. And as a result, let me skip the steps. We can speed up the process by focusing on what is important and doing the baby steps in this iteration is anything but important. You can do it on your own. So the pattern can be generalized into this value function. Please remember, n is finite at this stage. We are only realizing the pattern in the items of this sum. Just a minor correction, yeah? Yep. Hopefully it's correct. I'm just checking. Yep. it's all right. So this is the version for a finite n, and if n goes to infinity, we will have this value function if beta is lower than 1, it goes to 0, so it disappears. I think this is, yes, this is the only difference. And that's all. So by the repeated application of the operator of section 4.4, we get to this value function, and this is the fixed point of the operator for which this equation applies. That's all.